1400. The next speaker is Rachael Boyd, who will talk about low-dimensional homology of Coxeter groups.
Thank you very much. So yeah, I'm not going to talk about manifolds, but you can imagine that your manifold has a fundamental group, Coxeter group. And as Ben said, you have a group and you want to compute the homology. So that's what I'm going to talk about, is just some nice computations for low-dimensional homologies of Coxeter groups. It's on the archive, there's the number at the bottom. Okay, so Coxeter was around for pretty much the whole of the 1900s, and I assume he was interested in these reflection groups for most of that time. So he was interested in reflection groups of regular and semi-regular polytopes, which you can think of as high-dimensional analogues of polygons and polyhedra, roughly. He noticed that these groups, they all have, many of them have a similar presentation. So in 1935, he classified the finite groups that have this sort of presentation. And this notion was generalized to include infinite groups by Tits in 1961, and this is the definition that I will give. So to define a Coxeter group, first of all, you define a Coxeter matrix. So you take a finite generating set. So all of my Coxeter groups in this talk will have finite generating sets, but they will not be finite groups necessarily. So a Coxeter matrix is an S by S matrix, so you have a row and a column for each generator. The entries are 1 on the diagonal, and the matrix is symmetric with the off-diagonal entries either being a 2 or an infinity. Given this matrix, you can define your group via the presentation that it's generated by S, and that it has these relations. I really wanted to use this. ST to the MST is equal to the identity. So this says, because of the first condition, that all of the generators are involutions, so it's generated by reflections. And using that, the second condition can be written as a condition with an alternating product on either side, so having length MST. So when MST is equal to infinity, that just says that your relations, you don't have any relations that look like that. Okay, so the group W together with its generating set S is called a Coxeter system, and from here on the top, when I say W, I mean a W with a chosen S, so a Coxeter system. Okay, so you can package all this information in what I believe to be a much nicer way in terms of a Coxeter diagram. So this is a labeled graph for your system. It has the vertex set, the generators, and you put edges between them saying what the entries in the matrix are. So you put no edge if MST is equal to 2. So using the alternating product way of writing that, that says ST equals TS, so they commute. You put an edge with label 3, with no label if MST is equal to 3, and otherwise you write the MST on top of the edge. So yeah, you can put your whole presentation into this diagram, and by looking at this diagram, you can find specific subgroups called parabolic subgroups of your Coxeter group, which will be important in this talk, and they correspond to full diagrams. So by a full diagram, we mean we might have a Coxeter diagram here, and if in our subdiagram we take these two vertices, then we also need to take the edge between them with the same label. So here, if we take T to be our subset of S, given by these two vertices, WT, the group generated by T, with that generating set as a Coxeter system in its own right. And here are some examples of Coxeter groups. Okay, so our favorite example is the symmetric group. So if we let SI be the transposition I plus 1, then this diagram gives a presentation for the symmetric group. We have no edges between, for instance, S1 and S3 because the letters they talk about are disjoint, and S1, S2 make a 3 cycle, so we have an unlabeled edge between them. The dihedral groups are all examples of Coxeter groups as well, so everyone knows from their first group theory course that you can take the triangle, which is the dihedral group of order 6, which I call D6. It's generated by 2 reflections, and if you do one and then the other, then you have a spin of the triangle, so that has order 3. I've drawn here, this is the Cayley 2 complex for the dihedral group, so it has the generators, the vertices are given by the words in the group, and the edges correspond to multiplying by generator. You fill in a 2 cell when you see a relation. So here, STS is equal to TST. So this ST cubed at the end, we filled in this 2 cell. The Coxeter group acts on the Cayley-2 complex by reflections, and this will come back in a later example, which is why I included it here. So as I said, Coxeter classified the finite Coxeter groups, so finite groups which have these particular presentations are either one of the following diagrams or a product of 2 or more. So AN, we've seen that's the symmetric groups. BN is the wreath product of the symmetric groups with the cyclic group of order 2. So you can think of these as sign permutations. We go from n to plus or minus n. DN is an index 2 subgroup where all of your signs multiply to +1. And we also have all of the dihedral groups. So there are 4 infinite families, and there are also 6 exceptional Coxeter groups. So these all correspond to reflection groups of different regular and semi-regular poly. I mean, the AN, that's the symmetric groups, that's reflections of the simplex. BN is reflections of the cube. DN is reflections of something called a demi-cube, etc. So we're interested in the homology of these groups. So we did know some things before. So first of all, you can calculate the abelianization of your Coxeter group. It's z mod 2 to the m, where m is the number of connected components in your diagram after you remove both the even edges, so not the 2's because they weren't there, but the even edges, and the infinity edges. The reason why you can think of this as if you have an odd relation, you have an equality with an odd number of generators on each side. You can rewrite that as a conjugation. So everything with an odd relation, they're all conjugates, so they all have to map to the same, connected components have to map to the same conjugacy class. Howlett calculated the Schur multiplier of a Coxeter group. And this was done first in the case of finite Coxeter groups by Ihara. Which I forgot to include in the slide. So this is given also by 2 torsion, where each of these ni here are similar to above. We had the diagram, we had a function go to the natural numbers which counted connected components. So they can all be defined in terms of the diagram. And what I did as part of my thesis was 2 theorems about the second and the third homology of Coxeter groups. So the first one is a slightly nicer way, I think, to think of Howlett's theorem. So this is, again, for any Coxeter group. It could be a finite one or an infinite one. The natural in this statement means that with respect to full inclusions, if you can think of a category of Coxeter groups where your morphisms are full inclusions, on one side you have homology, which is a functor. On the other side, you create these new diagrams, which I will define on the next slide. You then think of these diagrams just as one-dimensional cell complexes, and you take some cellular homologies. And this also gives a functor to abelian groups, and this means the naturality means it's a natural isomorphism of functors with respect to the full inclusions. So this is theorem A, which I will go into in a lot of detail. Hopefully we'll be able to do the whole proof. Theorem B is the same. There are now 8 terms involving new diagrams that you make from your Coxeter diagram. There's one non-trivial extension which you can completely describe, and I'd like to point out that it's all torsion, and in fact Sarah showed, and you can see easily from the proof, that the homology of all Coxeter groups, integral homology of all Coxeter groups, is all torsion. So for what it's worth, here's theorem B. One thing to note is that the H1 and H2, they were all 2 torsion. Here, the last summoned on the top line, that gives you MST torsion for any MST that's bigger than 3, not infinity. So you can have any torsion in your third homology. Okay, so here's the definition of the new diagrams, and then we'll do a couple of examples. So given your Coxeter diagram, we're going to define the edge set and the vertex set of the new diagrams. So d odd is what you would imagine. You keep the odd edges, right? And you throw away all the even and infinity ones. The even, you throw away all the odd edges and the infinity ones. You don't add an edge for when you have the 2s. You just leave them as they are. And this decommuting is given by, so I call this decommuting because they look like 2 commuting generators. So the vertices of this diagram are all the pairs you can see that commute. And you have an edge between 2 pairs. Say you have S1 and S1 and T1 and S2 and T2. If S1 is equal to S2 and T1 and T2, you can see in your Coxeter diagram with an odd edge between them, then you create an edge between these 2 pairs in your diagram. And here are some examples using these new diagrams and the H2 theorem. So the first example is for this group A3 tilde. So this is an infinite Coxeter group. It is the reflections of the plane tiled by triangles. So you can think of the 3 generators as reflections in the 3 edges of some fundamental triangle. So here when we throw away the even and infinity edges, we have d odd being the whole diagram. When we throw away the odd edges, we're just left with these 3 vertices, and there are no commuting pairs because they all have 3 between them. So then working out from the top line, we only have h1 of d odd, so we have 1 z mod 2 for the second homology. For the finite Coxeter group F4, here we delete the 4, here we delete the 2 3s, and for decommuting we notice that S and U commute, and so do S and V. So here S is the same, and U and V have an odd edge between them, so we draw an edge. Here V is the same, and S and T have a 3 between them, so we also draw an edge. So we get 1 Z mod 2 for each edge in D even from the middle term, and we get a Z mod 2 from H naught of this diagram. So are there any questions so far?
So when you say like D even, D odd, or like D to dot, so you can get something which is not a group, right? Like for example, you get an empty set here.
Mm-hmm.
So what you mean, is it a group or it's not a group? So what you mean is the H0 homology of this object?
So you think about it as a cell complex, simplicial.
Just
Forget the labels,
okay.
yeah.
I see.
So I say cell complex because in the H3 formula there are some cells that you glue in.
Okay, so you view it as just a complex. I see.
Yeah. Okay, so the proof consists of realizing that we don't know that much about Coxeter groups in general, but we know a lot about the finite Coxeter groups. So we try and reduce the calculation of homology to just a calculation about homology of finite Coxeter groups. And we do this using the Davis complex and the isotropy spectral sequence, which I will now define. So the Davis complex is a cell complex which the Coxeter group acts on. It's created by, first of all, considering spherical subsets of your generating set. So that means that the parabolic subgroup that they generate is finite. Manuel, can I erase this? You've hidden the eraser. So you consider just the subsets which are finite. We've let the empty set generators generate the trivial group, so that's always included. If your Coxeter group is finite itself, then all subsets are included. If we have, for example, this infinite subgroup, then, for example, this would be a T which would generate a finite subgroup. We had this with the trivial group. So given the finite, all the spherical subsets, we can create something called the poset of spherical cosets, which is take those finite subgroups that they generate and take all their cosets in the Coxeter group W. So this is a poset because you can order cosets based on inclusion. And then the Davis complex is a realization of that poset. So that means the P simplices is given by chains of P plus 1 cosets that fit inside each other. So the Coxeter group acts on the spherical cosets by left multiplication, so it acts on the Davis complex by left translation. And I will give an example here. Okay, so here this is for the finite subgroup A2, which was the dihedral group of order 6. Hopefully you notice it kind of looks like my Cayley-2 complex that I drew. So there are 4 spherical subsets of the generating set, the empty set. Both generators generate a cyclic group of order 2, and the whole set. So we take all of the cosets and I put arrows between them if they include inside each other. Where we have a triangle of arrows, we fill in a two simplex. So S acts by multiplication on the left and reflects vertically, and T reflects this angle. So I'd like to put a refined cell structure on the Davis complex. And by refined, I mean there are less cells. I don't know. Here we let the cosets, which have of spherical subgroups which have 0 generators, be the 0 cells. The cosets of spherical subgroups which have 1 generator be the 1 cells. Here we can see EWT. This can be a 1 cell. It has 2 vertices. It has 2 elements, so there are 2 0 simplices including inside it. And so we continue in this fashion. We let WS, if S has size 2, be the 2 cells, and if we have a spherical subset with size P, we let that be a P cell. Okay, so this is my my refined cell structure for this example, and S and T still act on these cells. They don't fix them pointwise anymore, and I can't remember what else I wanted to say about the picture, so I'll just move on. We're going to come back to that picture later and do our example for it. So the next player is the isotropy spectral sequence. So to use the isotropy spectral sequence in this case, we need to know that the Davis complex is at least aspherical, it's contractible. So we're in good shape. And this is, the proof that it's contractible is done by noticing that it's sort of made up of translates of contractible chambers and that they glue nicely. It's something called a basic construction. I know what I wanted to say. I wanted to say that the 2 skeleton of this is the Cayley-2 complex that we saw earlier. Okay. So for a contractible G complex, the isotropy spectral sequence set says that there's a spectral sequence with E1 page the following that converges to the homology of the group. So on the PQ spot of the E1 page, we have the sum over orbit representatives for P cells under the action of the homology of the stabilizer of that cell with twisted coefficients. So this is whatever coefficients you wanted tensored with the integers, where if the stabilizer flips the orientation of the cell, the axis is -1. So for our example, we want to sum over orbit representatives. So we took cosets, and W acts by left multiplication, so we can take all the identity cosets as our orbit representative. Looking at this, we can see that the orbit of this 0 identity coset is all of the vertices, the orbit of this is these 3 WT cosets, and the orbit of this is these 3 WS cosets. We want to look at how, at the stabilizers of our cells. So we looked at the stabilizer of this is just the identity. S stabilizes this, but flips, acts as a reflection, so it changes the orientation, as does the identity. So actually, E and S, which is precisely the group WS, generates a stabilizer here, and here WT, the subgroup generated by T, stabilizes this cell with again T acting as reflection. So this is true in general. So for the Davis complex, the isotropy spectral sequence is given by, on the E1 page, sums over the orbit representatives of your P cell. So they were identity cosets, so you just need to identify the subgroup. So we had the P cells corresponded to subgroups where the generating set had order P. Now we take spherical things which have size P, and they'll give us all the orbit representatives for the P cell. The stabilizer of the cell EWT is exactly the subgroup WT. It's a coset, so everything in there will stabilize it. And this action here on the integers, since every generator is reflection, a word will act as -1 if it has odd length, and +1 if it has even length. So now we've completely identified the E1 page, and all of these are spherical subgroups, so they're all finite subgroups. So now we have an E1 page, which is the homology of finite subgroups with twisted coefficients. And this converges to the homology of the Coxeter group. And remember, the Coxeter group didn't need to be finite, for example. We could have taken this infinite one on the left. Are there any questions about that? Oh, here's another picture. So here now we're in good shape. This is the E1 page of the isotropy spectral sequence. Here we have homology of the trivial group. Here we have sums of homologies, twisted homologies of cyclic groups of order 2, which we can compute. Here, when T has size 2, all of the finite groups, they look like dihedral groups without an infinity here. So we have sums of twisted homologies of dihedral groups. And here, when T has size 3, well, we have to look in our diagram for 3 generators that generate a finite group, a finite Coxeter group, and we have a list from Coxeter's classification of finite Coxeter groups of what all finite Coxeter groups can look like, right? So we have to either look like something which looks like, we have to look for something which looks like a dihedral group cross a cyclic group of order 2, or maybe it's a symmetric group, or it could be the group H3. So here we have a finite number of cases for what we can have in this column, and it continues. So I wanted to tell you a bit about why different diagrams, sort of we create these new diagrams, but why are these showing up in the proof? So it converges to the second homology on this red diagonal and the third homology on the blue diagonal. And so for the second homology, these first two can be computed to be trivial, and so we just care about this group down here. There's a nice formula for the transfer map, which in this case on the bottom row is literally counting the numbers of cosets of the subgroups of that finite group of certain size. For H3, there are, apart from the first column, there are 3 things, which is why we have an extension in the formula, and that means that we also have to deal with some differentials and prove that they are 0. But for H2, I'll show you the proof. So this was, the top row here was the bottom row, and the middle is the red place, so we want to compute the homology here. And in fact, we're counting cosets, and the transfer maps will be trivial if there are an even number of cosets, and the identity on the Z2. So these are all sums of Z mod 2s because that's the integer mod out by the action. And it will be the identity if there are an odd number of cosets. So going from subgroups with 3 generators to those with 2, there's only one case where you have an odd number of cosets, which is where WT is a subgroup of type X, which I've actually already drawn on the board. So, and this maps non-trivially to the commuting pairs. So we've split this up into commuting pairs with an even edge between them that don't commute. So there's actually an edge there, and pairs with an odd edge between them. So here when we're looking at the homology in this place, we're looking at the co-kernel here, which is exactly the 0th homology of the diagram that I defined, right? These are the edges, right? And these are the vertices. We then have a Z mod 2 for every edge because these all go to 0. And the only thing that gets hit over here are vertices where the edges between them are odd. And this gives us the H, the first homology of the odd diagram. So that's the full proof for the H2 case. And then the H3 case is much more. I mean, there are 8 terms, so you can say it's 8 times more complicated. But I mean, for the H3 case, because you have to compute the differentials, you really need to know what some of the twisted homologies are here, and there's not a nice algorithm for working out. I mean, I said we know things about finite Coxeter groups. There's a quite nasty resolution by De Concini and Salvetti, which gets a bit nicer when you work with twisted homology. So you can use that to compute these groups here and so on from 3 above. But it's sort of a non-trivial amount of slogging. Okay, so this was the splitting. I wanted to end with, this is a table of homologies of the finite Coxeter groups. So even though this also works in the infinite case, I included this in the paper because it's sort of above H1, it's not really written down anymore what the table of the finite Coxeter groups are. And this sort of corresponds in part to Richard Hepworth had a proof of homological stability for Coxeter groups where you start with any diagram and you add on a tail. So this group was G0, including into this group was G1, etc. So he said this has homological stability when H star of G n minus 1 is isomorphic to H star of Gn when star was less than or equal to n over 2. And so using these, you can see this in the families An, Bn, and Dn. And using the formulas, you can see that for actually any group here, you get a little bit better. So H1 becomes an isomorphism immediately because you're not taking out any more even or infinity edges. H2 becomes an isomorphism from G3 onwards, where I think this would say and H3 was from G5. So this is present in these calculations here. There was a computer program that I'm unaware of, a gap computer program called HAP by Graham Ellis, in which you can compute also compute some small homologies of finite Coxeter groups, but I think it depends how good your computer is. I can definitely do these calculations faster than my computer can. So it's nice because you can really get, I mean, you're just working, it might be an infinite group, but you're often just working with a small diagram, so you're just working with small graph homology. And I'll stop there and let us have coffee.
Any questions?
You mentioned the computer, so can you also get H4, or I mean, either by computer or by hand, or?
So using this method, I'm pretty sure that you could just continue and work out H4, but it was sort of a case-by-case thing to see that the differentials vanished, and a case-by-case thing for each of the extensions as well, using different inputs. So,
And it's getting more and more complicated.
yeah, I think it's doable, but it would take more time than I'm willing to. But yeah, so perhaps I'd like to see actually what his computer program does. It's only for the finite Coxeter group, so it wouldn't. Yeah, sorry, maybe I didn't mention that.
Could you use this to give another proof of stability for Coxeter groups? By showing that certain sub-diagrams stop showing up once you've got the long enough tail?
Yes, I mean, definitely. You could for the first three, yeah, and then I suppose that your I suppose it depends how big your starting diagram is, right? But it's a finite size, so you would have a finite number of these spherical subgroups inside it, and then afterwards, yeah, the only ones that you would get would be the ANs, or maybe perhaps BNs or DNs coming from the tail. So I imagine that's actually doable. That's a nice idea.
All right, that's thanks, Rachel. Yeah.